I put this talk together is that a friend of mine up at SUNY Albany asked me to come up and give a talk, and I'd already given 2 talks up there, and he didn't give me a lot of time. So I thought I would talk to this group of physicists. They're all physicists. They're essentially don't really have any astronomers, and talk a little bit about the advances in astronomy that have been driven a lot by material science and detector technology and things like this that not everybody may be aware of, and certainly it impacts to some degree, at least the detector stuff, on earth sciences. So that's where this kind of came out, and then I started realizing, well, I should talk a little bit about how machine learning is starting to transform the field, databases, crowdsourcing, and all this kind of thing. So that's kind of how this talk came about. So I won't mess around, but I like to give a little historical background. Some of you know that I'm like a little history buff, so I like to talk about history a little bit. So let's talking about mirrors first of all, or if you prefer refracting or reflecting telescopes. And I think that almost everybody agrees that Lippershey and / Galileo were the first with, we're not sure of the exact size, I think, of the very first telescope they built, but they say it's around 1.5 centimeter, the aperture size, around this time period. And then these are some of the big leaps that were made as time went on. The Newton Hooke reflector, that was initially 3.3, and they got it up to 18 centimeters by 1674. The Herschel, what we call the 1.26 meter diameter telescope, incredibly large telescope for 1789. Although back then they measured the telescope size by the length of the tube. So he used to call this, I think, his 15-foot tube or 20-foot telescope, something like that. Something called the Leviathan, that was 1.83 meter, 1854. And then this telescope, which is very important, the Hooker telescope, 2.54 meter, that was built in 1917. That was the biggest telescope in the world until the Hale 5 meter came along in 1948. This telescope is still in use today, and it's an incredible telescope. The primary mirror is one solid piece of glass. It's probably the heaviest single piece of glass ever built by humans. They realized later that this was not a good idea, and they would hollow out the glass on the back side to keep the mirrors light, and that's how the Hale was built. And then, of course, came along the Soviets. They had to challenge us, and they built the 6 meter in 1976, although there were some problems with this telescope. The primary was replaced at least once, and there were some other issues, but it's still fairly large. And then, of course, another revolution came along in the early 90s when the first segmented telescopes came along, the Keck. This is what one of these segmented mirrors looks like in the Gran Canarias telescope in 2009. And then I think the next generation is going to be these super large telescopes, 30 to 42 meters in that range. We're not sure. A lot of it depends upon money and budgets. The Europeans, as late as 2 years ago, were saying it was going to be 42 meters, but as the budget goes down, the size of the telescope aperture goes down. Yes, sir.
How heavy is the Hooker compared to the Hubble, for example?
To the Hubble is about the same diameter, much heavier. I can't remember the number off the top of my head, but it's
like an order of magnitude.
Yes,
2?
It's like an order of magnitude heavier. Yeah, it's an incredibly
And how
heavy.
big? What's the diameter of the Hubble?
2.5 meters.
2.5.
Same as the Hooker. That's why it's a perfect question to ask.
Just by accident, okay.
You hit it right on the head.
Well, where did the Russians put their telescope?
This is in the Caucasus. It's just north of the Black Sea. Is that area? It's Karachay-Cherkessia is the name of it. I have a friend that works at the.
Is Azerbaijan or places?
Sorry?
South of Russia.
It's in southern Russia. It's it's north of the Black Sea and to the west of Georgia.
That's
And north of all these public areas.
yeah. That's where this famous astronomer Abartsumian was.
Yeah. Well, he was Armenian, but he probably
Armenia,
built this observatory. But this is not in Armenia. This is
No?
in Russia proper.
I see.
So these 30 and 42 meters, these are continuous. This isn't like virtual where you have it really, it's more than one.
These are segmented telescopes. They haven't been built yet, but the idea is they will be built in the
But it's
next decade.
continuous. I mean, I understand it's segmented,
Yeah,
but it's
but
like
they're
all
stuck
one
together.
thing. Yeah,
Yes, they're
yeah,
stuck together. Exactly. And this is what it looks like on a, by year and just on a linear scale. You can see this incredible increase. And then for those of us that log scales, you can see that the increase in size, assuming these last two are built, is going to be nearly as fast as it was in the very beginning of telescope technology, which is quite interesting in itself. And I think one of these two is certainly going to be built, either the ELT or the 30 meter telescope will be built, one or the other. So all these plots are numbers I pulled myself because I'm becoming increasingly not trusting plots that people put together and stick on the web for various purposes. So.
Yeah.
But I should say that telescopes, I think today they're not quite as much a part of our culture as they used to be, but when the Hale 5 meter was built, it was a big deal in the country. And back in October, it was the anniversary of the birth of its giant eye, the 5 meter Hale. And they talked a little about it. And just about a month before that, my aunt, who lives in Chicago, had been at a rummage sale or something and had found that some coasters or ashtrays that have the same pattern as the Hale 5 meter. And it comes with a beautiful little booklet, tells you all about that. I mean, imagine this today, they don't do things like this. So I thought I would pass around these things. Apparently, while I gave this talk, does it work? Yes. When I was giving this talk to the Museum of Natural History, one of the postdocs started looking these things up, and then he found out that there were 2 versions made. One actually was made for the World's Fair around that time, and it says that on the inner edge here, but unfortunately I don't have the World's Fair. I have a cheap ripoff, I guess. So, this kind of thing was a bigger part of our culture, and I think in a sense, although the Hubble certainly is the most well-known today, whether it's the same or not, I'm not sure, but I'm not sure how many replicas of the primary mirror of a telescope that they would send out like this today. Who would even know what it was? Okay, let me talk a little bit about detectors. I'll start with, of course, the eye and photographic plates, photophotometers, and I'll get to charge a couple devices. This is one of the photomultipliers that I actually use myself. This was from 1947, although I wasn't around then. The first observatory I used was still using this ancient photomultiplier tube already into the 1980s, which was quite incredible. Use dry ice to cool them. Okay, so quantum efficiency of the eye is not so high, between 1 and 10%. And the size is about 0.7 centimeters, unless you're someone like Arnold and you have a big head, then maybe his aperture is just slightly bigger. But of course, upgrades are possible. These days, maybe this isn't so science fiction-like anymore. I've heard more and more stories about them putting these kinds of devices in people's heads. Hopefully, they'll be in better shape by the time they do it. But this sort of first way to capture images, of course, goes back to 1826 with this camera obscura by Nipse. But I think the first, in terms of astronomy, useful things were these plates that came along by Daguerre. He used this wet colloidal process. The quantum efficiency was about as good as the eye. He took the first moon images in 1839. This guy Draper came along a year later and using a 13-centimeter reflecting telescope got an image of the moon after a 20-minute exposure. This is very difficult work with these kind of wet plates, of course.
Did you say the quantum efficiency was 10%?
I've read that it goes between 1 and 10%. I think it's wavelength dependent, obviously. Bond and Whipple were the first to get a star photo. That was of Vega in 1850, so only 10 years after. And then the first spectrograph, remarkably enough, already in 1872 by Sirius. And this technology would move very quickly. The spectrograph itself, I could give a whole talk on that. And this is the earliest known, that I know of at least the Daguerre image of the moon, 1851, with this wet process. Thankfully, they moved over to a dry process. Again, the quantum efficiency, not remarkable, 1 to 3%. Spectrograph, 1876. This guy, Henry Draper, got the first photo of the Great Nebula in Orion. And this guy, in 1883, is credited with the first objects fainter than could be seen by eye with these dry photographic plates. This guy was an amateur astronomer, built his own telescopes. This is what one of his early telescopes looked like. Hasn't changed so much. Amateur astronomers still build telescopes in their old chicken coops out back. And this is one of the images he made very early on of the Orion Nebula with this new technology. Then the first survey of the sky started taking place in 1887. This was not terribly efficient, but nonetheless it was the first survey. Had an incredible field of view, 2 by 2 degree. That was the field of view of the telescope. That's gigantic. That's larger than the diameter of our moon. Think about it that way. And this technology moved more and more. They built telescopes with larger and larger field of views. The largest in its day was, I guess, 1948 was this Auschen-Schmidt telescope, 4 by 4 degree field of view. It used 14 by 14-inch glass plates. And this is a case where they realized they could build an object with a very large field of view in the sky, and they could sort of pave the focal plane of the telescope with these photographic plates, either here or up at the primary, depending on which. And I brought along, as part of my show and tell, an image of one of those plates. So they would build these, they would take these photographic plates, And then they would make copies of the plates, and they distributed them to observatories all around the world. And this is how astronomers used to make finding charts from these plates. So when I started out, way back when, this is how I built finding charts. And I would run this thing off on the photocopier and then take it to the telescope with me. It's amazing how much it's all changed. And then it came with this very nice overlay, and you could use this to find objects that had been identified by the survey yourself. So these are from that 1948 telescope where they did these surveys. These are called Palomar Sky Survey plates. I borrowed this from Columbia University yesterday.
Is it kind of like USGS? So it's, they have done all parts of the sky. And
Yes. They did the northern hemisphere with Palomar, and then the Australians did the southern hemisphere. And then they used two different kinds of photographic emulsions, one in the red and one in the blue, so they get some color information in the skies. But the thing about it is that it's not USGS in the sense that it was a private observatory. So Andrew Carnegie paid to build this observatory, Mount Wilson and Mount Palomar, and it's still run by this private foundation, the Carnegie Foundation. So that's one thing that's kind of unique, I think, in astronomy, is that private individuals have funded a lot of astronomy, especially in the last 100 years. And before that, there were no national observatories.
But their data was free? It was just kind of the
Yes,
process.
this was free. That you just had to pay to have the place delivered, basically, and you paid for the process. But it was made to be relatively cheap. I mean, it was the only way to get finding charts.
What is special about the word paving? I mean, you always put the glass in the focal plane. Why do you call it paving?
What I mean is that you could fill the entire focal plane, and I'll come back to what I mean by that a little bit later when I get to CCD. So these telescopes were built for these large photographic plates to do imaging of these photographic plates. So that's what I mean by paving that focal plane, because it'll turn out that later we won't be able to pave it so readily with the advanced technologies we'll talk about. And of course, I just mentioned one other is my kind of favorite telescope in the world, the 2.54 meter. This again was built by the Carnegie Foundation in Chile. So they wanted a Southern Hemisphere observatory. It's a 2.54 meter, and it had, again, a very large field of view. And again, they took these large images of the sky with that. And Edwin Hubble and other people use these to classify galaxies with these plates from the Southern Hemisphere. Okay, so a little more on detectors. So the photoelectric photometers came along already in the late 1890s. So not too far after the photographic film came along. I think you can think about it as kind of a single element charge couple device. Not much in the way of digital output, paper tape if you were lucky. And although this is an optical talk, I have to mention that when I was reading up on these photoelectric photometers, I found out that they actually built some X-ray photoelectric photometers back in the late 40s, and they even used a used V2 rocket to launch one up as high as they could and do some observations with these photoelectric photometers and the X-rays of all things. Pretty crazy. And this is one built at the Paris Observatory back in the day.
So
But
they
then
were using the photoelectric effect before Einstein had figured out what the photoelectric effect
Yes,
meant?
exactly. But then along came charge coupled devices, and of course here now you finally see the quantum efficiency has gone up by a remarkable amount. This is wavelength dependent and materials dependent. I won't have too much time to go into that, but it all came about because of a discovery done at Bell Labs back in the late 1960s and early 1970s by this guy Boyle and Smith, who got the Nobel Prize in 2009 for the discovery, the 7th prize from this lab, I might add. If only universities could claim to have 7 prizes in a given university. It's pretty phenomenal. It's too bad that it's more or less fallen apart these days. But this is how the detectors changed in size. And here I'm being a little bit disingenuous in that up to this point, all were single element, single pieces of silicon, more or less. And then we started to build mosaic cameras of these things put together, which took off. So the most widely used today is probably the Sloan Digital Sky Survey, which I'll show you some pictures of that camera later. This was put on the Canada, France, Hawaii telescope. That's up at Mauna Kea. This is the Pan-STARRS 1 telescope. It's got 4096 CCDs that are 600 by 600 pixels in size. So this is a monster camera. It's designed for surveying the entire sky in about a week's time. That's the idea behind this camera. And this is going to be hopefully built also within the next decade. It's going to be 2,000 CCDs that are going to be 4,000 by 4,000 in size. It's going to be producing petabytes of data a week. This telescope, you can believe it.
So
So these people are looking for supernova or something?
They're looking for any variable objects in the sky.
Anything they can find.
Supernova, asteroids, you name it, they're going to be finding it. Blazars, you know, active galactic nuclei in galaxies, all this kind of stuff. But what you can see here is that the increase doesn't look anything like it has been on the telescope and the aperture size. The increase has not gone as fast as you might expect. And that's some limitations due to, of course, this technology limitations in a sense. But still increasing, even if a bit slowly in these recent years. So, but before these CCDs started getting big, we had to find ways to use these telescopes with these big focal planes. So I mentioned the DuPont and the Schmidt, they have these huge focal planes, but the first CCD detectors were tiny, right? So you imagine the first this is the focal plane of the Schmidt, and your first CCD detectors were tiny little things. So you were wasting all this light. So people started dreaming up ways to make use of that light. One of the most ingenious ways was to build what was called a fiber spectrograph. So they would have an image of the sky like this, and they would say, I'm going to go after all the extended objects in this image that I can down to a certain limiting magnitude. You would take an aluminum plate, you would drill the holes that would correspond to the, in this case, 128 optical fibers that you have that would correspond to those galaxies. You would have that plate shipped down to Chile in this case. This is the DuPont 2.1 meter. And then those fibers would be plugged into the plate, and then they would go to a fiber spectrograph. So you could collect for the first time more than one spectrograph of an object at a time. So this telescope could collect 128 spectra in one exposure. In 1 hour you get 128 spectra, which was a revolution for astronomy. So it was a way to use up this focal plane in a way you couldn't. So when this telescope wasn't doing imaging with these tiny little CCDs, they could make use of the entire focal plane with these fiber spectrographs. And I'll come back to them. But they were not easy to use, and they're still not easy to use. Okay, but as I said, people, once the detectors started getting bigger, people could start to pave the focal plane a little bit with these CCD detectors. And this is what is today in the Hale 5 meter. It's 620, 48 by 4096 CCD, as you can see, but it's only 12 by 12 centimeters. It's still quite small, but just to give you an idea of the scale of these instruments we're talking about, here's a guy putting in, this is what that circular thing would be fit to, and this is roughly the size of those CCDs, a little bit smaller. This is a photographic plate he's putting into the focal plane of the Hale 5 meter. And just to give you a scale of how small that is, this is the Hale 5 meter, if you come to visit it. So all that light is concentrated down in this very, very tiny area. Okay, and then, as I said, as the technology did get better and we could build bigger CCD cameras, people started paving the focal plane with these CCD cameras, and of course they had their fiber spectrographs too. So this is the Sloan camera. It's 30 2048 by 2048 CCDs. They built a 2.5 meter telescope at Apache Point that was designed just for doing a survey with this big camera. It was the first big survey of the universe done that was completely digital. Before that, people would scan these plates in digitally and then make surveys out of those. But these guys did everything digital from the start. So they would normally do imaging on nights when it was clear. We didn't have any of these awful clouds in the way. And nights when there were some light cirrus or wasn't so nice, they could use the fiber spectrograph because you don't need purely photometric conditions to get spectra of objects.
Where is Apache Point?
New Mexico.
Since you just mentioned nights, what do these things do during the day? Is there useful information to get them as well?
No.
None.
No. This object during the day, you can see that it's sitting out. First of all, normally you expect to see a telescope with a dome. This has a rollaway dome. So during the day, the dome is rolled back on top of the object, and they close it, and that's it. They try to keep one thing they do with these objects during the day is they try to keep their temperature very close to what the temperature will be during the observing conditions of the night. Because that's one of the biggest problems with the glass. The glass will expand when it gets warmer and cool when it's colder, and that messes up your imaging quality. So the idea is to keep that glass as close to the temperature it will be in the middle of the night, all during the daytime. So most of these places have air conditioning units and stuff like that to try to keep it cool. Okay, so yeah.
Since we touched the image quality thing, when was discovered the fact that the atmosphere affects the message?
I think that is quite old. I mean, seeing is what we call it in astronomy, and that's probably, well, I'm sure at least 150 years ago they knew about these things.
So they started looking at optimal locations all the way back then.
Yeah, and at first they made some mistakes too. If you go to Kitt Peak in Arizona, and I highly recommend you going if you ever get a chance just to see the telescopes there. The biggest telescope on that mountain until the, I guess, 90s was the 4-meter Mayall telescope. And they built this thing in a 6-story building because they had the idea that the seeing was a lot of it was caused by the ground. So they built this thing high up away from the ground to get away from the thermal stuff going on the ground. So it's this tremendous structure. They built an exact copy of it at Cerro Tololo in Chile. But it turned out that it wasn't necessary. So now all the telescopes are built on the ground. It's actually much cheaper than building a 6-story building in the middle of the desert. Okay, so of course with all of this digital technology,
To the data.
Yeah.
What is Angel? This guy was here in Colombia.
Roger Angel.
Roger, right?
Yeah, he's at University of Arizona.
I know. When he last year he went there, but he's a big shot in the mirror.
Yes, he is.
Well, what is his contribution? I don't know.
That's a long story. We can talk
Oh, really?
afterward about Roger Angel. Yes, he's done some important things.
Yeah, he did, right?
Yeah, absolutely. But there's some funny stories I can tell you about Roger Angel. So you seem
So his wife was working here at GISS.
I don't know that.
Yeah. Yeah, and he was working with the astronomy department. So then he went to Arizona to Kitt Peak.
Yeah, where he's been.
You cannot tell the story about it.
Okay.
Whatever.
So let me talk a little bit about data. I think this is where the earth scientists can relate to some of the things. I say from ASCII files to databases, and there'll be some revolutions in media storage. So, as I say, these CCDs gave us a fully electronic record, and thankfully, portable storage was catching up too, because you would go to a telescope in the middle of the desert in Chile, and you had to get your data from the telescope home. And when I first started, already still in the 80s, you really still use these 9-track tapes, which many of us old-timers still remember. I remembered incorrectly. I had this crazy idea that 6250 BPI tape was like a gigabyte in size, but that's just because I was crazy. 170 megabytes was how big that's how much data these big tapes could store back in the day. For those of us that remember Digital Equipment Corporation, they came up with a new technology called TK50, which was extended to DLTs. And eventually these DLTs went, well, the TK50s were 95 megabytes in the beginning, but they eventually extended these DLTs all the way up to 110 gigabytes by the 1990s. It was pretty amazing how far they could extend this technology. And then many of us remember these videotape type storage media that came along also just when I started going to Chile quite a lot, 8mm exabyte. You could get up to 5 gigabytes depending on the media, how it was stored. These digital audio tapes, everybody thought this was a revolution. Oh, I can listen to my music digitally with these cool little tapes. Didn't last too long, of course, because CCDs came along not too much later. The big problem with many of these technologies, of course, was they were these tape devices, and the tapes would get stuck, or you could read them 2 or 3 times, but you couldn't count on that. So usually when you left the observatory, you left with at least 2 copies of your data, in the hope that you would be able to read it at least once from each of them before you got it on the disk. But then along came the CDs, thankfully. Of course, the data storage wasn't quite as big, but the claim was that they would have lifespans of order 100 years. Whether that's true or not, I highly doubt it. But they certainly were better. You could read them more than 2 or 3 times without losing your data if you were careful and you didn't scratch them, as we all know. Blah, blah, blah.
Random access is nice too.
Random access was nice too. Yeah, this was all sequential access. Of course, this is all disappearing too. Then the DVDs came along, of course, also in the late 90s, early 2000s. But today, it all sits on disk in the cloud, of course. Nobody really brings their data along with them too much anymore. People thought for a while that, I think astronomers thought, oh, I'll be able to use these Blu-ray discs because they have high data storage, blah, 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 but that just didn't happen. It's all essentially moved to the cloud. Nobody runs around with tapes and discs anymore, which is good, I think, in a way. It's better than taking up half your luggage with data tapes on the way home.
Is that when you showed this thing?
Yes, I'm getting there, So, traditionally, as I say here, all of the data acquisition at a telescope was done by astronomers, and all the data reduction was done by those individual astronomers or their postdocs or their students, but a lot of that has really changed. I would say that most data today is collected in surveys on telescopes, or by what we call service observations. So you pay some astronomers to be slaves at a telescope for years, who collect your data for you. You put a proposal in, you tell them exactly what you want. They collect the data for you, and then they ship you the data by the web, essentially. that has been a big change for people. And at first people were resistant to it, but I have to say that I think it's been very good. I mean, you can't do it in every case, but in cases where it's possible, it is much more efficient. Because in the old days, you would go to the telescope, you knew what you needed, but maybe you weren't familiar with the instrument. So you would lose a third or half of the first night just getting up to speed on how the instrument worked and being efficient in its use, and the data acquisition systems would change every few years, so you had to become familiar with that. Of course, you have a staff astronomer there, he's on top of all that, so you don't lose any time. So I think that's certainly made the observatories much more efficient in many ways. But there are some other disadvantages to people not understanding these technologies too. It probably hurts us in the long run in some ways. But probably the first, I would say, completely digital sky survey that was built by astronomers was the digitized sky survey in the 1980s. So basically they took these plates and they digitized them and they built a CD catalog. There's two of these. This is only one hemisphere. The other one is sitting in my office. So 102 CDs. This is 51 CDs. So you could order that and it would show up and you could read them on your computer. And you could build finding charts, so I didn't have to go and pull these things out of the closet and deal with them. That made things a lot easier. This stuff was eventually put on the web, of course. The next was probably the 8 p.m. survey, as it was called. Just to give you an idea, this was a survey in the true sense. They not only built a catalog like this, but then they did object detection on the catalog. So just using these photographic plates of the full sky, they were able to detect 150 million objects, and they built a catalog from that. And that was the basis for the largest redshift survey of its time, the 2-degree field galaxy redshift survey, which was done in Australia, and they collected 250,000 spectra in that survey. And then the first, I think, really fully digital sky survey, I said it was the Sloan before, but that's not quite true. The first fully digital was this thing called the 2-micron all sky survey. They built a telescope in the northern hemisphere and the southern hemisphere, a 1 meter, 1.3 meters, sorry. They also built an object catalog. 471 million objects were detected in that catalog. And instead of releasing it like this, they gave you a DVD set, which was great. And you could order it, it would show up, and you get 5 DVDs of compressed data, which you could then unpack on your computer into a database of your choice, and then do your science, which was really...
2 micron? Why 2 micron?
It's a good place to look for active galaxies.
So it's near infrared.
Yeah, near infrared. It was 3 band passes around 2 microns. Of course, the full fidelity images, which it didn't release, were about 10 terabytes. But now all of this stuff is now accessible by database on the web, essentially. This was a recent paper that talked a little bit about that. And then, of course, the Sloan camera, which I talked about before. Just to give you some specs on it, that was a 120 megapixel camera with this very large field of view. So again, its field of view is about that of the moon. Again, they had a 600 multi-object spectrograph. And the latest data release, now they have data release 8, but this data release 7 had collected, by that date, about 30 terabytes total of data. And the database itself, which you could query, was about 3 terabytes in size. So this would fit today on a normal, a large workstation. Again, 357 million unique objects, and they had collected about 1.6 million spectra. This, if you had told someone that this was going to exist 20 years ago, no one would have believed you. It was quite fantastic. And of course, the data release 8, which is just released, has almost 1 billion unique objects detected. And this is what the footprint on this projection looks like. So it's a northern hemisphere object, so you mostly get northern hemisphere objects. Yeah.
Okay, I'll ask the question in case no one else knows.
Yep, please ask.
I don't understand the difference between the unique objects and the spectrum.
Okay, so these unique objects are just imaging. So this is what you would get. So they build a catalog based on the imaging. And then for the bright objects in the catalog, they go back and they collect spectra on the brightest objects. I'm sorry I didn't say that before, but excellent question.
I thought I was the only person.
Thank you so much for asking that question.
My
Yes.
God.
How many wavelengths do they?
They observe in 5 band passes. So if you look at the camera, which, well, I would have to go back, you can see the camera had different filters, basically. So it's a scanning camera, so it scans as the sky goes below. It stays in the same place when the Earth turns, and then it images objects in each of those 5 band passes as it goes past. So you get 5 colors, and then for a subset of those objects, they go back later and they collect spectra for those objects from around 3,500 angstroms out to about 1 micron.
But the spectrum must depend on what you want to do with them. You want to do star formation, you go to infrared. If you want to see quasars, you go to X-rays.
The survey is optimized for collecting galaxy spectra, essentially. But
Yeah.
you get a lot of stars anyway, so it turns out. Especially if you're looking in the galactic plane, because it's mostly stars. You can't see distant galaxies in the galactic plane. It's blocked by dust. So a lot of work has been done just
But
looking
you
at
want to
stars.
say that
and
it cannot be a universal spectrum. Depends on what you want to do. I mean, you have to look in a certain part of the spectrum to do your science.
Yeah, of course. Oh yeah, that's another thing. Okay, so the spectra, not only do they collect the spectra, but they measure all the lines in the spectra for you. So you can query the database and say, I want all objects in the database that have, say, forbidden oxygen 2 at 3727 angstroms that's greater than 5 angstroms in width. You can do queries like that. So you can do science based on what you expect from the spectra. So again, I don't have to go in and deal with the spectra myself, reduce it, and then pull all this information out. They do that all for me. That's again a complete revolution in the way observational astronomy is done. Okay, and these are just pictures I like to show you. Here's my little catalog over here. Here's a DVD. Here's a 9-track tape for you younglings who don't remember what they look like or never saw one. Here's a 4mm, 8mm tape. Remembrances. And this is what we deal with today. So this was yesterday and this is today. This is how you get data from the Sloan Digital Sky Survey. You don't ask them for a tape of the survey. You go to the database interface and you ask for objects that fit your science goals. So in this case, I asked for the position on the sky, its object ID. These are the 5 bandpass filters, U, G, R, I, Z, that have been corrected for a whole bunch of stuff which I won't go into. This tells me something about how the light is concentrated. These Petrosian radii tells me whether it's a point source or not. And then another great thing was that you could also, the objects would be classified. So these are called quasars. So here I'm looking for quasar objects. So the spectra's been classified as quasars, so I only get quasar objects. And then these 3 things down here called flags are quality flags. So that was another complete revolution with this database. With a 2-mass database, I mentioned the first survey, you only got, you could get some of this information, but in terms of quality, you either had it's good or it's bad. But in this case, they could tell you a lot more about how the data was reduced, where the 2 objects are very close to each other, and did they have to deconvolve the objects when they fit the isophotes? You can get all that information now. So if you don't trust that they're good about deconvolving objects that are close to each other, you can say, I don't want any objects that are near each other. You can ask for all kinds of sophisticated information. That's a big plus, of course, for people that want to take the time to understand the database, but of course it's a big negative for the science case when people don't. So in the early days of this database, there were claims that a lot of papers published with the Sloan were wrong because they didn't include any of these quality flags. So if you don't use any quality flags, you can get quite bad data and not know it if you didn't bother to take the time to understand the database itself. And in the beginning, people wouldn't publish these kind of queries. So nowadays, I think most people, they'll publish their queries, exactly what they got from the database, so people can reproduce the data. That's another thing that we have now. It's not like I have the data in my office and Andy has to come and ask for it. It's publicly available. They can run exactly the same query on exactly the same database and get exactly the same data and check it. And referees do this all the time, including myself, to see if people did the right thing. And sometimes you find out that people didn't. Or they didn't tell you some stuff they did to the data after they got it off the server. Then you have to ask them, can you please tell us what you did to this data, because I cannot reproduce it. But that has been really, really a revolution in a sense.
So is this discrete data by object? I mean, what if your object is not well defined, like galaxy? I guess they are not resolved, so what?
No, they are resolved. They're well defined. They have a point spread function.
You cannot see
Each object
single
gets
single stars there, so.
You can see single stars. Each object gets a unique object ID, 32-bit identification number, which is unique for each object. So when I produce this query, I not only get all this information, I get the exact object IDs for every object that's measured. Of course, there are some objects that they don't do a good job with. If it's very close, it's too big, and they can't deconvolve it very well, and that you can also eliminate those from here, and those would not show up in the way you're saying.
Yeah, but what I was trying to say, that galaxy is basically like a big object, and maybe you have some ideas what you can do with it, and so can you get just the image of it from the...
You can also get the images. Yeah, this is a full fidelity database. If you want the postage stamp of each object, you can get it. That's totally possible. That's where the 30 terabytes comes in instead of the 3 terabyte database. This is the database interface. But you could use this to get individual object IDs, and you can put those in and get the postage stamp images if you wanted. You can put them together and build things that are even as big as this if you like. And that's certainly been done. Okay. So I also want to mention that because, this change was actually driven, I should say, by a lot of unexpected collaborations. That Sloan Digital Skies Survey database, which was really unique for astronomy in its day, was the first one that was built. It was built in collaboration with Microsoft, with this guy Jim Gray, who was at Microsoft. It was a brilliant computer scientist. He passed away a few years ago. And Alex Saleh at Johns Hopkins and a few other people. The reason Microsoft got interested in this is because it was a large problem. It's open source. Anybody could get the data to play with it. And so they could publish that data and they could use it for their own purposes, in a sense. So it was great. It was a big plus. I think for the next generation, for these super big surveys where they're going to have petabytes of data, they're going to have to address it in a different way. And so there's now, again, another private-public partnership going on where they're building this next generation database. Because you're not going to be able to really download large chunks of the database. Today, you could still download hundreds of gigabytes worth. If you really wanted to reanalyze the data yourself, you can still do it today. It's just possible to download all the data onto your 3 terabyte disk, which people can buy today, and analyze the data yourself that you're really into. But that's probably not going to be possible in the next 10 years. I wrote a recent paper on this trying to explain why I thought it might not be possible. But for one, you may not be able to download a petabyte-sized data file in 10 years. It depends on how fast things move along. So just to download a petabyte now over a 10 gigabit per second line, it's 10 days. Okay. If prices continue to drop for disks, as it has over the last 20 years, a petabyte will cost around $200 in 2020. Whether that's the case or not, we don't know. It's about $40,000 now for raw disks to build a petabyte file system. But I think the real problem is that I/O, input-output, is really not keeping up with more type laws, in essence. So the growth in the number of transistors that you can put on a chip and other more type laws just are not keeping up with this kind of business. I mean, if you just think about how long it took us to get 100 megabit in this building, and we're not unique. Universities are not much better than we are, believe it or not. I'm not sure that we're going to have 10 gigabits to the desktop for everybody, or the next generation of that in the next 10 years. And you're going to have this problem of how do you get a petabyte from your disk into the machine's memory? I mean, you're going to have to build completely new bus systems. People are really worried about this thing. So one idea is that this database system, instead of you doing your query and pulling the data down, you do your query on the database, and it stays in a supercomputing center, and then you run your algorithms there. You would upload your algorithms to this database. And one idea they've had is to have kind of a R interface. R is a language that's used by statisticians a lot for what they call expert users. But I've been trying to convince them that this is probably not a good idea to stick to one language. It's better to build a wrapper like Python or Perl or something, and then you can call whatever language you need to from within that wrapper. And probably they'll end up going to that at some level.
Mike?
Yeah.
If you go back, I think that I got confused. You are discussing about I/O,
Yeah.
and then you also discuss about network connections. For
Yeah.
me, I/O is the communication from the disk to the computer itself.
Yes. So there's two issues. One is getting
Yeah.
the data
Okay.
from the disk to the memory, which is
Right.
that itself, that I/O, is a big problem. That has not grown at all.
For that, there was a revolution in the last couple of years with SSD disks.
Yeah. No, it's not a revolution. That's not true. The problem is the SSD disks are fast. But before that, you could have built RAIDs of disk and still get that throughput. The problem is getting it from the SSD into RAM.
Okay.
That's the problem.
Okay.
The problem is not like the throughput of the disk. The question is how fast can you pump it across the
Okay.
bus? So it's the bus I/O that's the issue.
I agree with that.
Okay, good. I'm glad you agree with something.
Yeah, actually, those are the problems which we have on supercomputer.
Yeah.
GFC now.
Yeah.
Even this supercomputer technology.
Oh, it's a big problem. They know about it. They know it's a serious problem. So I just mentioned a few other things that are going to go on for the future in terms of these big surveys. I mentioned this Pan-STARRS survey in the very beginning. Again, a 64-64 array of 600 by 600 CCDs. They're going to be pulling down. They pull down about 3 terabytes per night currently. This is another one that's pulling down about 1 terabyte that just started going on. I think they had first light just last week. And this is the the thing that we're hoping is going to be that's going to have first light around 2020. Again, about a petabyte per night. Different people give you different numbers for this, but the database size will be about 10 petabytes. So you can see big database, and the images, well, they estimate 60 petabytes, but it's probably going to be much more than that. These are numbers that don't make much sense to us today. In the same way that, again, 20 years ago, if you'd said you'd have a terabyte file system on your desk, people had said you were crazy. I think that's how you can think about these things. So let me talk a little bit about crowdsourcing. So I think it's a little older than most of us realize. The first kind of crowdsourcing used, at least for astronomy, is probably this American Association of Variable Star Observers. So these were amateur astronomers who had a passion for astronomy, and they were interested in contributing to science. There's a long tradition in astronomy of amateurs contributing to the field. And these guys have been doing this since 1911. Every year they publish a variable star catalog that astronomers could then use to go and find different kinds of variable stars and do science with them. I don't want you to get too confused with things like SETI at home. That's not really crowdsourcing. That's what we call volunteer computing. So basically, you just turn on your computer, you download their program, and it does its calculations without you having any involvement at all with the data. Crowdsourcing is where the individual plays some role in producing the data. Okay. So I would call probably modern citizen science. I would say post AAVSO probably started in 2000 with a NASA Ames Director's Discretionary Fund program that was built. They built a web interface where people could log on and identify and classify Martian craters from Viking orbiter data. These were the people that started that. I think another kind of famous one is Stardust at Home, and these guys, they took these aerogel images from tiny dust impacts from the tail of Comet Wild. They flew through this comet tail with this aerogel stuff. They collected all these particles. The thing came back to Earth, and then they had to analyze what these particles were, and they used people to try to figure out what the morphologies in this aerogel from these particles striking it were. So they could classify the particles that they saw in this aerogel. I know it sounds really strange.
What's an aerogel?
Aerogel is a kind of gel that was used, a special kind of super lightweight gel that they could use to collect these particles, basically. So they were suspended in the gel.
Fly paper.
Fly paper, you get it. Three-dimensional fly paper. Perfect. I'll put that up here.
You don't have to.
So do you, I mean, is there an element of subjectivity? Is that why people do it rather than writing a program to do it, or?
The programs aren't good enough. You need people to actually do the
How can you
identification
be sure
themselves.
the people are good enough?
I'm going to get there. Excellent question, Anne, as usual. Okay, so this is a project I have used the data from. So in 2007, a project was begun called Galaxy Zoo. And the idea was to classify those galaxies that they found in those imaging surveys of the SDSS. So you could look here and you would try to classify objects on this survey. The largest by eye professional catalog to that point was about 1,400 objects. This was an astronomer sitting down and classifying objects as spirals or ellipticals, how much the arms were descended, whether it was irregular, what it looked active, all this kind of stuff. It was about 1,400 objects, which is a lot for an individual. It's time-consuming and unpleasant kind of work. To date, these people using the public, they've classified over 1 million objects in this catalog. So they've completely revolutionized the field. So Anne said, well, how do you know they're any good? It's a really good question. So they've been very careful about getting multiple observations per object by distinct individuals. So no single object in that catalog has been viewed less than 14 times by different people. And they rank the people on how good they are at classifying things. Okay? So you can find bad apples very quickly in the system. So it's the same kind of thing. You have a web interface, an image comes up of the object, and then you get some choices on how to classify that object. And some people are hardcore into it. It's probably the perfect thing for someone with Asperger's to get into, I guess, or something like that. They just love doing, classifying. And some people have discovered some unique objects doing this. There's one called Hannes Voorwerp, which was a Dutch school teacher who found this weird object when she was classifying things, and she got her name on it and decided she wanted to become an astronomer at the end of the day. So she's doing a PhD in astronomy now. So we're increasing the number of astronomers.
What was this
That's good or not, I
object?
don't know. It was a galaxy that had, I think that they had passed through each other. essentially two galaxies that passed through each other, and it had a burst of star formation, and then left an echo from that, and they could see some strange colored gas in these images from this object. So they've been very, very careful about that. And then once they had this very big database of objects, then they could go back and do what we were talking about before, and use machine learning algorithms to automatically classify. Because the problem before was that the biggest database we had of professionally identified objects was about a couple thousand, maybe 10,000 objects max. But you really need a comprehensive training set, because galaxies are complicated objects. They're not, you need millions to be able to classify them correctly with a machine learning algorithm, in a sense. So they've had some success with that. So I should say, maybe I'll say it again later, but in these, these over 1 million objects, they estimate that the amateurs are better than 90% as good as the professional astronomers at doing this. That's what they claim in the paper. And the machine learning algorithms are about 90% as good as the amateurs in total. So not bad. We're kind of getting there. This project was so incredibly successful that other people wanted to get on board. So now they built something called the Zooniverse, where you can do all kinds of things. You can do planet hunting, looking for transits in the data, or you can transcribe old weather logs. That could be useful for this building, right? Transcribing old weather logs, finding out what weather was like 100, 200, 300 years ago in different parts of the globe.
There was a guy who got a PhD at University of Washington doing that.
Yeah, there you go. Ancient lives, reading old papyri. Maybe you're good at reading ancient Egyptian or Greek, so you can read old papyri if you like. So it's sort of taken off in a way. So if you're into it, go to the Zooniverse website. You type it in, you'll find out exactly what's going on.
I'll go back to the Galaxy Zoo thing.
Yeah.
If you have several groups of people, and by several this can mean on the order of hundreds,
Yeah.
building a separate machine learning automated classifier.
Sorry, I don't understand.
If you have several automated classifiers built independently. And
You
then-
mean you run several
and then
automated
you run-
classifiers using the data from this survey?
Yes.
Okay.
Can you rank them on their success rate and then try to use them to identify new objects?
Yes, in theory, you could do that. That's not been done so far, but that is certainly a possibility. I mean, the success rate has to be a little bit higher, I think, for them to make a lot of use of that. But in theory, yes. I mean, they've done that. They look at the objects that the classifier doesn't work in and see what those look like, but usually it's objects that are poorly described to begin with. So, and there's a lot of data, so it's hard to do follow-up on these things, in a sense, to go find out what they actually are.
Well, the only thing you can do is that you reclassify with all of them the already classified ones.
Yes.
And then measure the success rate.
Yes. Well, I'm getting there. I'm going to show
So
you
you
some
said,
numbers.
I have a last
Yeah,
question.
one more.
There were 1 million here. You said before, I think some of these surveys contain like 400 million objects or something.
Yeah.
So they're about, I see.
They're getting there. I mean,
0.25%
eventually it's going to go.
of
But I mean, with these automated classifiers, using this training set, you can then classify all billion objects, or whatever the size of the database is, at this kind of 90% level. I mean, that's what they have done. That's where they've gone.
Mike, I guess there are two approaches actually to using machine. Like the one which you mentioned that it's machine learning technique. It's like neural networks, I guess.
Yep. Yep.
But it's a lazy person approach. Other, I guess more correct approach is basically try to figure out physics. I mean, try to look at your object and write a program with image recognition and sort of like classifying it by.
You're right. Igor, they've been trying to do this for 30 years, and they have failed miserably. This is the most successful by orders of magnitude. Just to give you an example.
But anyway, I guess eventually that approach with.
It turns out the human face is much easier to work with than galaxies.
Oh.
But I still believe that having unclassified objects is worse than having badly classified objects, but they are marked as such.
We can talk about this more.
You're very
Otherwise,
specific
I'm never
data
gonna finish
quality.
this.
It's a sequel.
Okay, so I said I was going to talk a little bit about machine learning. I touched on it just a little bit. I think this is another thing that's happened in astronomy that's changed quite a lot. I think it's prescient in a sense because the 25th anniversary of the Journal of Machine Learning was just this year. And these are just some heroes of mine. Reverend Bayes, probably the only Reverend I admire in a sense. Gauss, of course, and his buddy Legendre and Adrian, who discovered least squares method. Of course, Gauss wasn't good about publishing stuff. He actually developed least squares in 1795 to predict the orbit of Ceres, the asteroid. He didn't get around to publishing it until 1809. In the meantime, two other people beat him to the punch. So that'll teach you to publish your algorithms on time. Shannon, of course, the information theory guy, also super important for us. But I would say that, obviously, given these very large, complex, multivariate databases, which I've talked about now, people are having to use more of these machine learning and kind of data mining algorithms to deal with them. So just to give you some numbers of how it's changed in the literature, there are at least 3,700 papers with the word Bayes in the title or abstract, so using Bayesian methods. You can think about it that way. Large numbers of citations for the most popular papers, and it's been increasing in number year by year. So here's some numbers that I pulled out. Well, actually, this is not mine. This is from Roberto Trotta, who gave this talk in 2008, and showed if they're normalized at the same time, you can see the increase of the word with the word Bayesian in the paper and the title has increased much faster than all papers in astrophysics, thank goodness. But I think he said that by 2020, all papers will have the title Bayes. And astrophysics. if this continues. But I did my own kind of checking up on things. So here is a plot of the number of citations per article with the word Bayes in the title or the abstract. You can see a lot get between 1 and 10. Here's the 1 and 10 citation, so people get 1 for most of the objects, 1,100. But some papers get incredible numbers. 480 for this Richardson, 576 Robin. This guy Lucy is probably the most well-known in astronomy. He has 919 citations for this paper. He is the guy who developed some deconvolution methods that were used for the first Hubble Space Telescope images when they realized that the mirror was deformed. So that's one of the reasons. But this guy's paper is so important. He gets a citation every couple weeks, at least every couple weeks. So this number keeps changing. I think it's now like 950 citations.
You know the Lucia was here in Colombia.
I don't know if it's the same guy or not. This is the paper.
Leon.
This is
Leon.
Pittsburgh. Okay, so it was the same.
Leon Lucia, yeah. That's the
So
one.
many connections. All right. So here you go. Iterative technique for rectification of observed distributions. But
Bayes
just
is not in the title.
I said title or abstract, and here it is.
Good point.
I just
Listen
want to
carefully.
say how quickly it was published, 2 months.
Yeah.
Yeah.
Back in the good old days. Yes, 1974. So again, I think this is showing that these techniques are accepted by the community in a way that, again, we might not have expected 20 years ago. And here's some other ones. So titles or abstract with neural networks, there are 1395, quite a number of citations. So I think this is probably the most well-known machine learning technique in astronomy. Here's with data mining, 4,700. You know, data mining is so broad. Machine learning, that's a little bit better, 288. And then 100 with the self-organized mech. This is a much more obscure method, but again, I'm impressed that there's over 100 papers with even this kind of obscure classification method is what this is, in a sense. It's like an advanced neural network. So not only are people using these kinds of techniques more, I think part of it is because there have been people that have been running conferences on using these techniques. And in fact, this one, Statistical Challenges in Modern Astronomy, is running every few years. He's run 5 conferences. The last one was just this last spring in 2011, and he publishes a book every time. And they also have run 7 astrostatistics summer schools that don't always correspond with the conference. So graduate students can actually come and learn how to do statistics in astronomy, which has been incredibly useful for the field in ways that I couldn't begin to go into. But of course, I have to do some self-promotion here. So this is the book I've been working on with some colleagues editing, which is Advances in Machine Learning and Data Mining Astronomy. I said it should come out in February, but it's probably going to come out in April at the rate that our chapter authors are getting their proofs in. But this book came about because I was talking to some friends about these kind of techniques and how they were coming along, and we decided to put a book together with contributions. So the first 2/3 of the book are astronomers that have used machine learning techniques for specific applications. So astronomers in different fields can go and see how these techniques have worked, and they can, of course, communicate with these people if they want to learn more about it. And then the last third are really advanced machine learning techniques written by people that are experts in the field. So, you know, going through a complete discussion of, say, neural networks and where those have taken us and all kinds of different techniques. So I think it's the right time for a book like this, in a sense. So we'll see. Maybe it'll sell 10 copies. So I just thought I would talk quickly about also this paper, which is this machine learning paper where they used the Galaxy Zoo data from the public to build their machine learning algorithm. So here they use sort of an artificial neural network. They use the morphologies from the volunteers, what I would call output I, and then they use some of the parameters that they get from the photometry of the galaxies from the database to train those to see if they can get out the right classification scheme. So they build a neural network where the inputs are these things from the Sloan Digital Sky Survey, and the output is the galaxy classification. So as I said, they do about 90% as good as by eye, and here you can see that for early type galaxies, it's a type of galaxy that looks like an elliptical galaxy. There about 92% of the objects can be classified accurately with this machine learning algorithm. For spiral galaxies, about 92%, and then what we call point source or artifact, these are your unknown objects. They're also very good at realizing they can't classify them at 96%. And these are some of the inputs. They won't mean much to you guys, but these are some of the different inputs that were used that they found worked to get this classification to work.
You said that they are very good in knowing that they cannot classify them.
Yeah, well, that's important. It's
That's
good to know.
Yeah, that's important. Yeah.
Yes,
Yeah,
that's
so
really good
this
to know.
90% meaning that 10% are errors, or that 10% are objects which they say they cannot classify.
Yes, exactly. 8% are objects they cannot accurately classify. They have to put limits on how good they go, but this 92% is what they call their gold sample. You can also go to the silver or the bronze sample if you want, and you want to be a little more sloppy, because your science might say that.
Yeah, but I mean, this 90% they say that they can classify and they're really, really good.
Yeah.
For 10% they say that they just cannot do this, or they are not.
Yeah, the algorithm doesn't work very well for those 10%, probably because they just don't have enough inputs. I mean, one thing in this paper that's frustrating is they say they use all these different isophotal inputs from the Sloan, but they don't tell you where they came up with them. So I don't know if they picked them out of a hat or what they did. This is a research problem. Someone needs to go through and optimize this, and no one's done it yet. It's something I've been thinking about doing but haven't had the time.
I guess that the 1 million objects already classified by humans are the easy ones, right?
Well, I mean, the million objects, they've been classified as either spiral or elliptical or not classified, not classifiable. So I wouldn't say they're easy. It's just that they have a limited number of volunteers. And that was only in the first, I think that was 1 year of the project, and the project continues. So they're going to have another data release, I think, this spring. And probably the sample will increase by at least a factor of 2 to 5. I don't know the exact numbers. I haven't seen the papers yet. But it's popular. It's growing. I think eventually they'll classify them all. I hope. Good idea. Okay, so I think I've talked a little bit about how I think the culture's changing. One maybe you don't realize this about astronomers, but we not only have to apply for funding grants, we have to apply for telescope time. So we have to apply twice as often as most scientists, and you have to get the travel funding too. So even if you get the time, you may not be able to get the telescope, you might not have the funding. Another plus of all this is, again, as I said before, you avoid some specialized instrument knowledge as an observer. I don't really care how the instrument works. I just want my data, right? And I have to say that it was back-breaking labor to run these fiber spectrographs back in the early 90s when I did it. And I said there are some positive and negative aspects, because you lose some institutional memory in the community as a whole about how these things work, and it becomes kind of a sect that does the instrumentation itself. So that could be bad in a sense, of course, as well. But I think that in many ways it's better for science. So you have more time to think of good questions, right? You can submit your query. Takes about 10 minutes. You download your data in 2 minutes, and then you can write your paper. I know.
Analysis.
Sounds crazy. Sounds crazy. I know, but I didn't say how long it took to write the paper. But let me just give you an example for myself. That's the best way to do it, right? So here's my PhD. I spent 2 years in Chile collecting spectroscopic redshifts in the Bell cluster galaxies, or compact clusters of galaxies. As I say, incredibly specialized instrument knowledge. The detector was a photon counting detector. It wasn't even a charge coupled device. I won't go into it. It was a crazy thing, but it had its advantages. I used this fiber spectrograph, and we had incredible problems with instrument calibration, sky subtraction, all kinds of stuff. Heavy use of time and labor. These plates were actually, we sent the sky chart to them in Pasadena. They drilled these aluminum plates, these big aluminum plates in Pasadena, and then they shipped them down to Chile to the observatory. For a 3-night run, you'd have to show up 3 or 4 days before to prepare for the observing run, because you got these plates and they would have 3 different fields on them, drilled holes, and you had to use a marker and label each of the holes for each of the fibers you would plug in, so you knew which object was which on the fiber spectrograph. It was a mess. It was a mess. And extremely long nights. So you had to plug the plates beforehand. You take your observation. You unplug them all. You plug the next set in. You do this 3 times, and in the night you have to sit around and collect calibration frames for hours on end. I mean, these are 15, 16, 17-hour nights. It was,
Michael, you look very young, so what does that mean?
What does what mean?
Then.
Then, yes. Well, this was 20 years ago. 20 years ago.
20 years ago.
So that's what I mean by then. And then 1 to 2 years, reducing the data to some usable format for my thesis. So the data, again, was very hard to deal with, even when I got back with my little 4mm DAT tapes. Okay, and this is here's a little close-up of the fiber spectrum. You can see the lines that we drew on here for each of the fibers. Each fiber had a number on it. And for that run, we would use the green marker, and you'd have to line up that fiber with that particular number for that marker. It was tough work. But then I got 128 object spectra in 1 hour exposure instead of taking 1 hour exposure per object. So it was a revolution in a sense. And this was the output image. This is what the spectra looks like. These are night sky lines. But here are some emission lines, oxygen, some forbidden oxygen lines, the Balmer jump. You can see for a lot of the objects
What
up
are we
here.
looking at here? I'm sorry.
Sorry?
What are we looking at?
This is the spectrum. So this is the red end of the spectrum, and
Okay.
this is the blue end of the spectrum. So each one of these is a
Absorption
galaxy.
I thought it was like a carpet weaving thing.
Yeah, I know. It's what is it? It's a good question. So each
Yeah, I
one of
just
these is a
didn't know
spectrum.
what-
So this is what you got. This is what you got home with you, and you had to extract the spectra from this crazy image. They're not even straight
Right, it's true. Yeah.
because of the instrument. So how about today? I say by today I mean this year. So this is a paper I wrote earlier this year that uses the SDSS, the Sloan Digital Sky Survey Data Release 7, came out in October 2008. The Galaxy Zoo, the first data release came out in February this year. I was waiting for it to come out. They gave all these morphologies for SDSS galaxies, like I said, about 1 million. And as I said in that paper I showed you before, they had all these isophotal parameters, which they claimed you could use to classify the galaxies with. So I thought, oh, I'm going to use them to try to do some science. I'm going to take those isophotal parameters and see if I can use those to make another kind of prediction about the object. So what I wanted to do was take those 5 band passes I talked about before, those 5 colors, and see if I could predict the recessional velocity of the galaxy without having to use a spectrum. Normally you use a spectrum to calculate the recessional velocity. You see the Doppler shift of the lines. But I wanted to use those 5 broadband passes to do that, because I've been doing that for several years for several kinds of projects. So we wrote an algorithm to do the regression for that, to make the prediction from the 5 band passes to the estimate from the actual Doppler shift from the spectrum, and that became publicly available. We published that in 2009. So once this was released, I built a cross-match catalog in about 5 minutes. And then once that was done, I wrote the paper in 2 weeks. So within the time that the data was released, I had a paper out in 2 weeks, received March 25th, accepted April 21st, published May 1st. So that's a record for me, I should say, for the time that data
That's
was
without referees.
That was a referee report. It was a letter. It was only 3 pages long.
Even so.
3 pages long. But still,
Even though,
And not over a weekend.
amazing how fast. That's because all this stuff was public. It was fast. I didn't have to do it myself, right? So here's my thesis. I collected on about 40 digital audio tapes. It was about 100 gigabytes, plus 4 years of work, and you get out this nice plot. I won't go into what the plot is, but
what against what?
these are measured emission lines, one against the other, and I classified the objects whether or not they were active galactic nuclei, they were called, or not. Because I was looking to see if these kind of active galaxies showed up in these very dense clusters of galaxies. Turns out they don't, but that's what my thesis was all about. The last project, the database was about 30 terabytes, but not sitting on my desk. I say plus 1,000 years of labor. Well, if you add up all the Galaxy Zoo people and everything they did, plus all the time built into the survey itself, the Sloan-Digital Sky Survey, all the people hours that were used over 10 years to build that survey, it's almost immeasurable. 1,000 years, I'm probably, 1,000 person years, I'm probably being conservative. And I could produce some regression plots, basically. So the data compression and time compression is completely distinct. In this project, I didn't have time to do it this week, but one thing I wanted to do was try to reproduce this plot from the Sloan, and I'm sure I could produce this same plot better than I did then, because all of these quantities are measurable in the survey in a day. If I had a full day, I could reproduce this plot instead of taking 4 years. So I want to wrap up because I'm way over. Jeez, too many questions. I should say that I think we all realize, especially in this room, that all these challenges are not limited to astronomy. All these challenges from this overload of data. I mean, Science Magazine had a whole issue about data just earlier this year. And here's a whole book on what they call the fourth paradigm, this data paradigm, which I can highly recommend. It's free. It was published by Microsoft. How people are dealing with this in different fields. But I would say it's not just limited to science. I think it's also in the humanities too. This is a book I finished reading earlier this year, where a historian uses everything from history, sociology, anthropology, archaeology, carbon dating, geology, genetics, everything to try to figure out one of these questions that there's never a good answer to. Why the West rules for now? Why is the West technologically more advanced than the East? And why has it been so for the last couple hundred years? And he's able to use all these things, again, because a lot of this stuff is public now. And you can make some advances, in theory. But I don't think all of these changes are going to solve all of our problems. I don't want you to think that I believe that. Here's a paper where they talk about 6 what they call provocations for big data, problems where people take these large data sets but don't understand them very well and apply inappropriate techniques to them and then get out garbage. I think we've all seen papers like that. And I think this quote from that article is very nice, like raw data is both an oxymoron and a bad idea. The data should be cooked with care. Again, that won't surprise many of us here. So I think I have covered all this. Science, we all know, is becoming more data intensive. I think, especially in earth sciences and in space sciences, that's definitely the case. And we're trying to explore new collaborations to deal with this data, as you can tell. And I think it's leading to ways of rethinking our methodologies. And I think programs in astronomy and physics are going to have to really think about these things. How to teach people probability theory, statistics, machine learning, data mining, and all of those things. Right now, that's a deficit in most of the programs. Most times, people only see probability theory when they get to quantum mechanics, at least in the physics program. And that's really not the first time you want to see probability theory. And there's almost no discussion of statistics, except in terms of thermodynamics or statistical mechanics. And again, that's a little too late to be dealing with high-level statistics, I think. But I think it's clear that all this is, in the end, going to affect our productivity. I think that's one of the reasons why, for better or worse, you see more papers published, at least in astrophysics, as time goes on. The data is easier to get access to, and it's easier to publish papers. Whether they're good quality or not, that's another question. So thanks for your time.